I think I am recording. Yes, I am recording. All right. So, let's talk about my first paper. Today I'd like to talk about my first paper. And this paper looks at a few things. First, the big picture. So, suppose you have a big city with a large traffic network, and you look at the way cars use this city. The decision of each individual driver might impact, in a small way, the outcome for all the other drivers. So this is a complex social system where each driver is not independent of every other driver. Now, how might we try to think about the efficiency of a road network? In particular, how might we think about the efficiency of a road network dependent on the individual choices of drivers? Because if these drivers weren't actually making decisions, then we might just think of them as a flow, almost like a fluid. But perhaps they aren't quite that. And so how would a driver make a decision? How does an individual in a vehicle choose where to go? Well, presumably they have a place where they start and a place they must reach. And so they could think of those as an origin and a destination. And each driver has their own origin and their own destination. But we need some more. To speak of efficiency, we need to assume that each driver has a goal. So they all have a different origin and a different destination. Though there will be a lot of overlap, because to get from one place to another, we will often need to take similar roads. And then oftentimes what we might assume is that drivers wish to get there in the shortest time possible, that they will make choices to reduce their travel time. So this is the basic setup. We assume that there are many origins, many destinations, with a lot of overlap, and that individually drivers make choices to minimize their travel time. So then what is efficiency? Well, efficiency would be, to a single driver, the extent to which they can minimize their travel time. And if we take a more system perspective, the individual driver is influenced by all the other drivers. So the efficiency from the perspective of a single driver is enhanced in this system's perspective by the effect that the decisions of the other drivers have on the first driver's decision. So if I want to get home, but on my way home, I must cross a highway for a short period of time. The efficiency with which I can get home is influenced by the drivers that pick that highway, that are on that highway in that moment in time. So again, it's not independent. So then, what if all the drivers are trying to minimize their travel time? Will they make choices that collectively contribute to each other's efficiency? So if I try to minimize my travel time, will I make a choice that still allows you to reduce your travel time or not? Will I negatively impact your travel time? And then if we look at the system level, in the aggregate, perhaps the average of all travel times, if we are all minimizing our travel times, how efficient is the entire system? What is the average travel time of the system? And could we do better? Could it get better than that if we were able to coordinate? So this kind of tension is one which is captured by the so-called price of anarchy. This is a concept from game theory, a mathematical discipline close to economics, which evaluates the efficiency of a system with interacting agents in terms of the worst outcome if everyone is, say, minimizing their travel time, and the best possible outcome if everyone could most efficiently coordinate with each other. Is there a difference, right? If there's no difference, then we can allow we sort of have some confidence that if we allow everyone to minimize their travel time, and they are successful in doing so, that they will actually get to the best outcome for the system. But if there is a difference, then this might be an indication that if we allow everyone to minimize their travel time and they are successful in doing so, that we actually don't get the best outcome for the system. So it's almost like there is some room for improvement, you could say. There is some potential to get a better outcome for the system, and for many people and for many individuals involved, many drivers involved, by intervening. So this is why this is called the price of anarchy. So what is the cost that we incur by not intervening at all, sort of a state of anarchy? And there's many ways that this could be interpreted. But we will be looking at this today in part because one of the fundamental assumptions that we've made so far is that these drivers could minimize their travel time. What does it mean that you minimize your travel time? Well, it means that you make the choice that minimizes your travel time. So that means that you need to know what choice that is. And it also means that you might need to know what choice everybody else is about to make, given that others' choices affect your travel time. Now, this might be a reasonable assumption in some contexts. For me to know what everybody else will do. But it's quite unrealistic in a system like a dense traffic system. So packaged in with these ideas is the assumption of rationality. That agents act rationally. But this is something which is often brought in question. And however, there aren't always very good alternatives to the assumption of rationality, though there are certainly many flavors. Behavioral, heuristics, biases. And one such flavor is learning. And it is increasingly relevant and popular because there are a lot of learning algorithms that are successful, powerful, and being deployed in the real world. So these learning algorithms can kind of give us a model of what it actually might mean in a mathematical way to learn. So specifically, we will think about Q-learning. And Q-learning is a reinforcement learning method which is based on a feedback loop where an agent tries, receives a feedback, and updates its beliefs based on the feedback that it receives. And Q-learning is a very successful reinforcement learning method, though being quite simple. It's been used, for example, to beat the Atari games. DeepMind implemented it to beat all the Atari games. And it has since been extended in many forms to address more complex problems. So Q-learning is a really interesting reinforcement learning method to look at because it is, on the one hand, simple and on the other hand, powerful. So what is Q-learning? Suppose you have an agent, and this agent can make two choices, A and B, and we're going to represent the value of these two choices with a real number. Then the agent makes a decision with a policy, which we call pi, so it looks at its numbers, and with the probability 1 minus epsilon, it'll choose the largest number. But with the probability epsilon, it'll choose an action at random. And then this action is played, the environment provides a feedback, and the agent uses this feedback with this function, which we call the Bellman function, to update its values. However, there are always going to be more than one agent. And this is why we have a game. And the particular game that we'll be looking at is a game that can model traffic. So in our game, suppose we call this the Braess Paradox. It's a network where we have three actions. On the one hand, agents could go up, they could go down, or they could cross. And on some of the edges, they receive a fraction, a reward which is a fraction of the other agents using that path. So if more agents use that path, they incur a higher cost. Now, if they split evenly over up and down, that's the socially optimal configuration, and the average is 1.5. However, if all the agents cross, the average is 2, and this is what we call the Nash equilibrium. At the Nash equilibrium, the agents aren't incentivized to do anything different. And so we see that the social optimum is 1.5 and the Nash equilibrium is 2 in terms of average travel time, where we want less average travel time for the system, and for a single agent wants to minimize their travel time. And this discrepancy we can think of as the price of anarchy, this difference. So we will be playing this game with many more than 2 agents. In fact, we might play this game with as many as 100 agents. And so each of these agents will be picking an action and repeating, where each of these agents has 3 values in the background which represent its beliefs for the 3 actions. They pick a value, they pick an action, they test it in the network, and then they can update their beliefs about all these actions. And so what we find is that when these Q-learners repeatedly interact with this simple, very simple road network and update their beliefs over time, we find that they end up in these interesting oscillatory patterns where they move sort of between the social optimum and towards the Nash equilibrium with this gradual worsening and rapid improvements. So they never actually get stuck and in that efficient Nash equilibrium with an average travel time of 2. They move towards it slowly, and then after a spike, there are these drastic improvements. So what is actually happening here? Well, the Q-learners only update the value for the action that they take, which means that they will still have in memory some of the old experiences that they had. And this delay between the updating and the memory allows them, in a way, to remember how things were and to revert to behavior when things get worse. And what happens is that we actually form groups over time. And so if we look instead at the variance, this is the variance of their Q values, we find that it aligns really closely with these spikes. So the variance grows very large, or grows very small, just before a spike, which means that beliefs converge, right? Beliefs, so the difference in all the beliefs, all the Q values, grows very small. So it's almost like a group is forming that thinks something quite similar, just before many of them change their opinion. And then the variance grows and gradually decreases, somewhat following the gradual increase in average travel time. And it kind of makes sense that you have this group formation which leads to large changes, because when many agents think a very similar thing, it is much more likely for a small change in the system to lead to a large change in behavior, because everybody thinks something similar. Now, what we find is that this is quite dependent on the exploration rate. So this is the frequency with which agents do things at random. So if we compare our agents to just a simple, what we call an epsilon rational agent, which would be an agent that plays the Nash equilibrium strategy most of the time, but deviates from the Nash equilibrium strategy with a small probability epsilon. So it adds some noise to their decision making. we find that for a very small amount of noise, they are basically Nash equilibrium players, and as we increase the noise, their average travel time of all these players decreases. And this is because in the Braess Paradox, any deviation from the Nash equilibrium leads to an improvement. There's a particularity of this system. And so when the agents are fully random, they actually have a rather low travel time. But fully random behavior isn't particularly realistic. So this end of the spectrum is not as interesting. But so when we compare these noisy rational agents to learners, this is what we see. That in the low end of the exploration rate, the Q learners deviate significantly from these noisy rational learners, and their average travel time is rather small, or can be rather small. So this is really the region where this coordinated behavior that we were seeing earlier happens, where these memory effects and delays can allow for this group formation, which enables the system to rapidly switch between a gradual worsening and a rapid improvement. So if we come back to the original question of the price of anarchy, the price of anarchy can be redefined for these learners, for these Q learners. What is their best and worst behavior in a network, a road network, like Braess's paradox? So why would we want to redefine this at all? Well, perhaps because we think that the assumptions of rational agents with perfect information about all the other driver decisions might not be realistic. Perhaps it is more realistic to assume, in the context that we consider, that there is some kind of learning, that there is some kind of iterated repetition and dynamic. And if that were the case, then using learning as a benchmark might actually give us a much more accurate idea of the inefficiency of such a system, like a road network. From our simple model, or in our simple model, we see that actually the inefficiency of this road network is lower if we look at this, so maybe a price of Q learning, as compared to the price of anarchy that was established for rational agents. So what other situations might it not be so reasonable to assume that agents are rational, and instead that they are learning? I think there's probably many such situations. So there are some unanswered questions that I wasn't able to address yet in this video. However, these are topics of future work of mine and very relevant. But just to give you a hint of what that might be, right, we get this reduction in travel time for these Q learners for a very particular value of the exploration rate. Now, what guaranteed us that in a state of anarchy that all these learners would actually have that exploration rate? Might they not set their exploration rate to 0, in which case we might get no difference between the original price of anarchy and a price of Q learning. So that requires a different kind of analysis, and But it is the topic of one of my future papers. And to give you a hint, we find some interesting results that suggest that rational algorithm designers that can rationally pick the exploration rate might actually pick it in such a way that these coordinated effects are present. And for that we need to look at the metagame. But I'm getting ahead of myself. So that's all for now.